Hello and welcome everyone. I'm Dr. Muhammad Darwish, and this is only a small discussion about the design calculation of ion exchange resins or ion exchange reactors based on the breakthrough curve. So this is the main equation for designing the ion exchange, which is called the Thomas kinetic equation. And as we can see, we have ln of C naught over C minus 1, okay, equals minus K C naught times V over Q plus K Q small naught times M over Q. And this is the definition of each abbreviation. The C naught is the influent solute concentration. It will be expressed in milligram per liter or mill equivalent per liter. Same goes to the C, but this is the effluent solute concentration. We have the K, which is the rate concentration, which means that how many liters per day for each equivalent of the solute is passing, and this is a rate constant. And we have also Q naught small, which is the maximum solid phase concentration of exchanged solute, and this is determined in equivalents per kilogram of resins, which means that how many equivalents of the solute is removed for each kilogram of the resin. Okay, and M capital is the maximum, M is the mass of resin. M is the mass of resin in kilograms. And V is the volume of solution passed through the column. And Q is the flow rate. Okay, Q is the flow rate. So V is the volume of solution, not the volume of the reactor or the column. Okay, it is the volume of solution which is passing through the column, and Q is the flow rate. Okay, so based on this equation can be plotted as a linear equation, as you can see, in the form of y equals mx plus c. So y is this term, mx is this term, and v, you can see v is the x, which is the variable here. Okay, and all this term is represented by m, which is minus k c naught over q, and the last term is represented as c. So this data can be obtained from a laboratory experiment or a pilot scale, and it can represent the breakthrough curve. Okay, so this is representing the breakthrough curve. So the same flow rate, okay, in terms of the volume of the bed per unit time, okay, it should be used for both pilot studies and full-scale columns. So using the data from the laboratory or using the data from the pilot scale, we can apply it to a large scale design for the ion exchange column. Okay, this is an example. Let's see. So we have an electroplating rinsed water containing 49 milligram per liter of zinc. This is to be treated by an ion exchange column to meet an allowable concentration of 2.6. Okay, so this should be the effluent concentration, 2.6 milligram per liter. We have a laboratory scale column and provided the breakthrough data shown in the first two columns of the table below, and these are the data provided from the lab experiment. Okay, and those two numbers is going to be applied for the large scale application of the ion exchange column. Let's see here. We have the diameter of the column in the lab was 1 centimeter. The length was 10 centimeters. Okay, the mass of the resin in the moisture basis was 5.2 grams, and the water content is 17%. Here's the density and the liquid flow rate we have here, and this is the initial concentration. For the large scale, the flow rate is going to be 36,000 liters per day, and the hours of operation is going to be only 8 hours per day. And there will be, for the large scale, there will be a regeneration once every 5 days. After 5 days, we are going to make regeneration of the resin. So the resin should be enough for 5 days at least. After that, it will be exhausted and we'll reach the breakthrough point. So we need to make regeneration. So the question asks you to determine the mass of the resin required. Okay, so the mass of resin required. So let's see. Here is the data provided from the lab experiment. we have the volume of solution, okay, the volume of solution passed through the column. So for example, for the volume of solution when it was 0.32 liter, okay, the final concentration was 2.25, from 49 to 2.25. okay, when the volume increase, of course the concentration will increase because we are reaching the breakthrough point. Okay, 1.92, so the concentration reach 37.02 of the solute. Okay, so from this column we can convert to milli-equivalent per liter. So we convert the milligram per liter to milli-equivalent per liter, and we should know how to do it using the molecular weight of the zinc over the valence of the zinc, which is 2. Okay, so we can produce the column for each concentration. We can have the second column, which is the C, in terms of milli-equivalent per liter, and then we can have the third column, the fourth column, which is the C naught over C minus 1, in order to have the final one that will be plotted. Okay, so we will have this one, and finally we can take the len, okay, the len of C naught over C minus 1 for each value, and we can calculate it, and we can get the answer, and we can go and plot the V, okay, V versus the len C naught over C minus 1. So this is the plot graph. So on the x-axis we have the V, as you can see. On the x-axis we have V, and on the y-axis we have the len of C naught over C minus 1. Okay, we plot each point here, and then we got a trend line. We draw a trend line. So we use here Excel software. You can use any other software, or you can use plot or graph paper. Okay, so and then we can get the equation, which is y equals minus 2.5173x plus 3.6548, and the r square was very good, which is 0.9835. okay, so this is a linear equation. We can see the value of m and the value of c. Okay, so the value of m equal minus 2.5173, and the value of c equals 3.6548. So how are we going to benefit from this equation actually? Okay, so this equation is the linear equation, so we can compile it with the Thomas kinetic equation. This is the original form of the equation. Okay, so here we can see that we have the three terms. We have y, we have mx, and we have c. So this is m, and this is c, and this is y. Okay, so we can say that k c naught over q equals m. Okay, and k c naught over q equals 2.5173, and of course the minus will be deleted with the minus here. Okay, so minus with minus will be positive. Okay, all right, so we can and here we have to convert the zinc concentration to equivalence. Okay, to equivalence. So the equivalent of zinc equals 49 over the molecular weight over the valence. So we have 1.5 milliequivalent per liter for the 49. So the 49 milligram per liter, here it will be converted to 1.5 milliequivalent per liter of zinc. Okay, so here we can this equation we can solve it for k in order to find the value of k. We know the value of c naught, we know the value of q, so we can find the value of k. So if you solve this one for k, okay, using the concentration as 1.5 milliequivalent per liter for c naught, all right, so you have the value of k as 13.207 liter per day per milliequivalent. Okay, because here is a milliequivalent, so we have to put it as milliequivalent. All right, so this is the value of k. Okay, so here we got the value of k. Left here is the value of q naught. Okay, so from this term we have this term equal c. So K Q naught M over Q equal the value of C. We know the value of Q, we know the value of K just now. Then how about the value of M? Okay, M is the mass of resin. So mass of resin is 5.2, it is given, but we have to take out or substitute, or we have to draw out the water content. The water content is 17% of the weight. Okay, so it's 70%. So the dry real weight, the actual weight, is the 4.316 grams. So we are going to work on this one. Okay, because the water is not workable in the ion exchange, so you are only using the dry resin actually. Okay, so here you can solve this equation for Q naught, and then you can get the value of Q naught, which is 0.505 milliequivalent per gram of resin. So that means each 1 gram of the resin is able to remove 0.505 milliequivalent of zinc. So here we have the data of the lab scale, so we can use it and calculate for the large scale, except that we are going to change the flow rate into 36,000 liter per day. And don't forget that we are working only 8 hours per day. What does that mean? It means that you're going to calculate the volume of solution, okay, the volume of solution passing through 1 day, and then it tells you that each 5 days is going to be the regeneration. So the regeneration is going to be after 5 days, and in each day we are operating 8 hours. So you know how to calculate the volume, and after getting the volume of the solution, it's only left for you to calculate what? To calculate the mass of resin. Okay, so this is only the key point about how to solve this example, and then you can find the final answer. I leave it to you to calculate the final answer. If you want, you can send it by comments or by WhatsApp. It's up to you.